So, welcome back students. We are basically discussing mainly three different strategic viewpoints, transformation based, functional group based and starting material based, and I said many times that these three strategical approach should be combined together because these three approaches are very similar to each other. Now, today what we will be going to discuss, we will be talking about different kind of approaches which we have already talked about. Mechanism based strategies will deal with some individual case study or some particular problems where a specific mechanism of a name reaction or a unique transformation will help you to design the pathway. And I said repeatedly that mechanism based strategy means that you need to be familiar with the mechanism, and just by looking on that what kind of transformation is desired from you. Now, initially I will give you a target molecule. The target molecule structure I am first drawing, and then find this was the target molecule which is required. Now, the starting material I am giving it to you. The starting material is basically a furyl carbinol system. This is the starting material. Now, if you do the structural analysis of the target and the starting material, you will find that basically what you need, you just need a oxidative rearrangement of this furyl carbinol system, furyl carbinol system. Now, if you remember in our transformation based approach, we talked about a reaction whose name is Akma-Toich transformation. It is basically a name reaction. And now, I say if you have this prior information that Akma-Toich transformation basically uses a furyl carbinol as a starting material and give you a kind of oxidative rearrangement to a 6-member ring product. Now, this ring product also having a oxygen here, this structure was initially not written. So, if you find the number of carbon and things, everything is same, but you need a little bit more oxygen here. There are 3 oxygens here, there are only 2 oxygens here. So, now what I am trying to do, I will do a simple straightforward retro to disconnect this molecule, and then we try to figure it out how this target can be correlated with the starting material. And if I say this is simple FGI, this FGI what I did, you basically having a alpha beta unsaturated ketone as well as a lactone, and this ketone probably you can reduce it with a mild reducing agent which you already discussed, maybe a Luce reduction. So, Luce reduction only touch the alpha beta unsaturated ketone. So, these things we already. Next retro which I am now going to formulate will be something like this. I said that this particular lactol, this is basically a lactol can be oxidized to lactone by a simple FGI, oxidative transformation. Now, if you now know that this Akma-Toich transformation is basically, now you can correlate that Akma-Toich transformation here, that this kind of furyl carbinol system undergoing oxidative rearrangement through this name reaction which is Akma-Toich reaction. And eventually visualization is a bit difficult until and unless you know the mechanism very clearly. So, now we will try to explain how this mechanism is operating. We have probably explained earlier, but still we talk about this mechanism. A furyl carbinol was taken and initially this was basically subjected to MCPBA, a oxidizing agent. So, the initial stage, the one of this furan double bond ring undergoing a epoxidation reaction, and this epoxidation reaction was initially takes place, and then it was basically the ring opening of this furan oxygen occurs through this way to give you a species where oxygen now become oxonium ion, and then you have this remaining part, it is there, your epoxide basically now opens up to give you a oxygen minus alkoxide. Now, this O minus helps to discharge its electronic thing and opens the furan ring in this fashion. So, basically you will be having a aldehyde here and here you get the corresponding ketone. So, basically now furan ring is opening to a 1, 2, 3, 4, 1,4 dicarbonyl system, 1,4 diketo system, and this was basically a very characteristic reaction of furan carbinol system or furyl carbinol system. Now, if you closely analyze this structure, this particular structure in the MCPBA medium, this medium is already acidic because the corresponding metachlorobenzoic acid is there, and this benzoic acid what it does, it basically helps to protonate this aldehyde, to helps this by this H plus donation. Okay. And then this alcohol at the extreme right hand side, it now attacks in a nucleophilic fashion to this electrophilic carbonyl oxygen, which is basically activated through this, because there you are having aldehyde as well as ketone. Aldehydes are much more reactive than the ketone, but then this aldehyde, this OH alcohol attacks here, you basically get the lactol, which is our main product. Sorry, this structure was wrong, you need to draw the structure again. You see the ring, so 1, 2, 3, 4, 5, 6. So, there will be a 6 member ring will be formed. You have this OH, this double bond 2, 3 is there, and then you are having this ketone and this methyl. So, basically this methyl is this methyl, this OH is this oxygen, this reacts here. So, CHOH it is a new bond, this 2 3, this 2 3 is basically this double bond, and then you have this CO. So, in this way now you are basically getting the lactol. So, this after you get the lactol, then if you have this lactol which can be easily oxidized by PCC. So, once you now oxidize this lactol to PCC, you will now get the lactone. Now, this lactone, if you see the structure, you will basically having a carbonyl group here, a carbonyl group, simple ketone, and you are having a ester carbonyl. Now, obviously, Luce condition, sodium borohydride and cerium chloride will give you the reduction at this particular activated ketone carbonyl, and you get the target molecule whose structure was earlier given. So, which is the entire pathway, it is purely mechanism driven. mechanism driven. So, if you know the particular mechanism of the Akmat-Weich reaction is a mechanism driven pathway. You can basically also categorize the entire strategy in either transformation based approach or starting material based approach or functional group approach, no matter, but eventually if you are quite sure about the mechanism, then the mechanistic pathway which will tell you the furyl carbinol can efficiently be converted to corresponding 6 member lactone or 6 member lactol, basically hemiacetal, which can be oxidized back. The similar way we will be analyzing another interesting reaction. We said is mechanism or transformation based strategy. This particular was pretty interesting. We say the target molecule is something like this, where R could be any alkyl group, and now I am saying the starting material, let us say R is here a benzyl group CH2 pH, just for a case study, and then I am saying your initial starting material is 2-methyl pyridine. Well, it looks very interesting. It basically gives you an idea that you basically need to have a selective reduction of other pyridinium pi electron, so that this double bond remains unaffected. Your prerequisite, I am giving you a prerequisite or precondition, that no hydrogenation or lithium liquid ammonia like Barch reduction you cannot use. Okay. So, this is absolutely important prerequisite. So, you cannot use something like this. Now, this particular problem was solved very nicely. Eventually, the starting material was given this, and the R group probably a CH2 pH means that somehow you need to add extra CH2 pH group. Now, to substitute pyridine are very good reagent, if you or they can easily react with a base like butyl lithium, and eventually you can generate this CH2 minus Li plus very easily. And this CH2 minus, to act as a nucleophile, you react with a very good electrophile benzyl bromide to initially get the CH2 pH. So, which we will now call it as a R. Okay. So, this R part was initially done. Now, next what we will be doing? You have to do the selective reduction. In addition, you need to put a extra methyl to this nitrogen. So, initially the approach was, first it was subjected to methyl iodide in a methanol solvent. Now, methyl iodide, what it does? It basically give a quaternary ammonium salt or quaternary pyridinium salt. So, now nitrogen is plus. These are remains similar. Now, eventually this species, if you have a close look, is basically a iminium species. This particular C and double bonding is basically iminium species. So, iminium species are basically this kind of species, N iminium species. So, iminium species are electrophilic in nature. You can add any nucleophile, it is basically like a aldehyde or carbonyl compound. Instead of oxygen, you have a C double bond in nitrogen, and as this nitrogen becomes positive, nucleophile can attract to this carbon. Now, here initially what we will do? We will be using a mild hydride reagent like sodium borohydride to give a hydrogen source, and this hydrogen source basically will attack to this electrophilic carbon. So, eventually then what happens? So, initially this nitrogen will now takes this hydrogen. This is typically done. So, once initial this reduction was done through a iminium kind of thing, now see next how you can do. The earlier structure, there will be a methyl thing, there will be a methyl thing. So, now this quaternary methyl now become a trivalent methyl, your R is here. Now, you have a methanol as a solvent which is also a proton source. So, now what happens, this oxygen sorry nitrogen lone pair will try to give this kind of resonances, and this minus will now abstract the proton from this methanol. So, basically nitrogen will again become a quaternary thing, and this time it will become a iminium species again, iminium species again. Now, by virtue of this reactivity, we know that iminium species are electrophilic in nature. So, you again subject to a sodium borohydride, and this sodium borohydride now attacks on this carbon, and nitrogen charge will be now neutralized. That is fine. So, now this is the final product. So, you may now argue that, said again this nitrogen, is it possible to form another iminium ion? The answer is no. Initially you have a conjugated system. So, that is why the iminium ion formation is quite possible, like for this case, initial case, the lone pair gives this electron donation, it is having a allylic system, it comes here and it abstracts the proton. So, iminium ion formation is possible only twice. Now, this case there will be no further iminium ion formation, there will be no further iminium ion formation, and that is how the reaction now will complete. As there is no iminium ion formation, the reaction will be now completed, and this will be isolated as the major product or the final product. So, if you see the entire reaction, the reaction basically goes through a simple formation of a quaternary salt, quaternary ammonium salt, which is iminium and electrophilic in nature, and you just simply add a sodium borohydride as your hydrogen source, which basically gives a nucleophilic hydride. This thing is a nucleophilic hydride or hydrogen, and once you have a 2 round of successive iminium ion which can be attacked by the nucleophilic hydride or hydrogen, then the reaction will stop, because further iminium ion formation is absolutely not possible. So, your mechanism will basically dictate you that where to stop and what product you will be expecting. We will be trying to give you a similar kind of very interesting reaction. Now, this reaction will be just on the similar topic, the topic which I have just explained, chemistry of iminium ion. This reaction basically is named as Jinke reaction. It is a pretty old reaction, sometimes it is referred as Jinke reaction, or sometimes it is named as Jinke aldehyde synthesis. Now, this reaction is named in this way because it was invented first by the scientist Jinke in long ago. The synthetic potential of this reaction was not explored earlier. in traditional retrosynthetic terminology, you can basically write this reaction in this way. The target molecule I am writing in the green color of this pen, and final product is basically this kind of conjugated aldehyde is the main product, which is the target molecule. The starting material was basically this one, and the reagent which is normally supplied a diamine. This diamine was supplied as a reagent. And eventually this reaction is very interesting. This reaction, if you see the mechanism, is a pyridinium nucleus, and pyridinium nucleus normally they react either 2 position or 6 position by nucleophile. So, in this case, once the parent pyridinium ion is there, your nucleophile is R1NHR2, this amine. So, this amine first attacked at this carbon of this 2 position, and then basically it basically comes here, this quaternary nitrogen is quenched. So, basically have this AR, and then this nitrogen acting as a nucleophile, this amine R1 R2. R1 R2 could be anything depending on your choice. Now is very interesting. I am not sure whether you know it, but I am probably this is a very interesting reaction. Is a pericyclic reaction, 6 pi electrocyclic ring opening reaction. I am sure all of you have studied this reaction. This reaction occurs in thermal fashion, 6 pi electrocyclic ring opening. So, the rule for the selection rule is 4n pi thermal and photochemical. Thermal is conrotatory and photochemical is disrotatory. 6n pi or 6 pi, thermal is disrotatory, photochemical is conrotatory. So, selection rule for pericyclic reaction or electrocyclic reaction, I am sure all of you know it. So, now if you are doing this particular 6 pi electrocyclic ring opening through a disrotatory fashion, you will find that now this reaction basically occurs in this way, and now you will be basically having this pyridinium nucleus will be now clipped, to give you a 6 pi open system, which is basically nothing but a imine, it is a imine. Now, this imine can simply be hydrolyzed through a acidic workup, and then basically you can get a this conjugated aldehyde, which is now generated. Now, this Jinke reaction has a significant usefulness in the field of organic synthesis, and probably if I do a target molecule something like this, I say I am giving you a target molecule, you have to apply a Jinke reaction. The target molecule, first let us draw the structure. I am saying this target molecule is having this structure CHO. Now, this is a target molecule. You have to identify the starting materials, and your key hint is key transformation, you have to use the Jinke reaction. Now, the Jinke reaction mechanism we have explained, now you try to analyze. We said that this particular part, this alpha beta unsaturated, this conjugated aldehyde, you can construct by Jinke reaction. So, basically what you need 2 amine. So, this is one part of this amine, this is one part of this amine. So, now you formulate how you can do this reaction. So, if you have this particular pyridinium species as a starting material, and the amines, what are the amines basically you need? You basically need this diamine, this indole based diamine CH2 N H and this allyl. So, this amine, this is basically, if you go back to the general slide, this is the group which is R1 and this is the group allyl group which is now R2. So, in this way this R1 and R2 will be R1 R2 NH. So, which is now simplified as R1 R2 NH, and this R1 R2 NH, this nitrogen attacks to this 2 carbon, this pyridine, and then you get the initial nucleophilic addition. Initial steps are nucleophilic addition, and then you have this 6 pi electrocyclic ring opening, 6 pi electrocyclic opening, and then at the end you are having this imine hydrolysis. So, this all steps together will give you this Zinke reaction, which is very useful, and Zinke reactions are absolutely useful in the field of organic synthesis. We can use this reaction very efficiently. So, we will continue our discussion on the mechanism based strategies, and we will be basically try to give you more uncommon reaction whose mechanism probably you are not sure about or you are not familiar. We can discuss that mechanism first, then we will try to figure it out how this mechanism based strategies will address how a specific target can be achieved from a given starting material. So, we will come back to the next lecture. Till then, goodbye.